With that, I will now like to invite Professor Vikram Deshpande to please come to the stage and introduce our Prager medalist, Professor Fleck from Cambridge University.
Thank you very much. I don't need to say many words to introduce Norman Fleck as a Prager medalist. Many of you, if not all of you, already know his work. But just to briefly say, Norman did his PhD in Cambridge working on fatigue crack closure, a topic that not many people do these days. But he then very quickly moved on to sort of the modern frontiers of micromechanics, working with John Hutchinson, Bernie Budiansky, and a whole series of eminent mechanicians on things like strain variant plasticity, microbuckling of fiber composites, and a whole range of other topics. He has mentored and sort of supported a whole generation of young mechanicians, both in Cambridge and all over the world. They're faculty members, his students have been faculty members all over the world, etc. For this, he has received many honors, which I will not list because that might take too much time. But I'll list a few. He is a Fellow of the Royal Society in the UK, international member of the National Academy of Engineering, as well as the Fellow of the Royal Academy of Engineering, and many other such honors. His work in the last sort of 10 years, or maybe a bit more, has been largely on micro-architected solids, and more recently on multi-phase micro-architected solids. And that is the topic that we will hear on from him today. And without much further ado, I hope you all welcome Norman for this Prager Medal lecture.
A bad time to forget your password. Right, okay. Well, thank you very much, Vikram, for that introduction, and thank you SES for the Prager medal. Maybe I shouldn't say this, but in the words of Alan Cottrell, who I knew when I was a graduate student, Alan Cottrell said, "Don't give me any more medals, give me money." So it's very nice that SES understands that and gives money as well as medals, so I thank you doubly. Today I want to talk about multi-phase, multi-scale, multi-material lattices, and ask the question, are they worth all the effort? Well, they're worth the effort in the sense that they've produced a bunch of nice papers, I would claim, and so that's one metric for worth the effort. I'll come on to show you that biological materials often are multi-phase interpenetrating lattices. This work has been done over the years, very much inspired by Mike Ashby, Laura Gibson, who I think I would strongly recommend to read their monograph. And I think it's always worth to read what has been done before reinventing the wheel, so I think it's worth people really spending the time to look at that early work. The work I'll report has been done with a bunch of graduate students and postdocs, and some of these postdocs have gone on to great things and become Prager medalists themselves. So Vikram, my close friend and colleague, I'm very grateful of your help over the years. Today I'm going to talk about, first of all, I'm going to talk about some examples of multi-material lattices from biology, chemistry, and additive manufacture. I'll then essentially focus on a much simpler problem of a lattice which is constrained in its volume by putting an incompressible core, think of it as an viscid incompressible fluid, and ask the question, does the volume constraint affect the behavior of the lattice? So it's a constant volume response, cell by cell, constant volume. So no communication, essentially, of the liquid, or equivalently incompressible solid of zero deviatoric strength. How does that affect the response? One can embellish that and go on and put in strain hardening behavior of both phases and so on. But what I want to focus on is the purely geometric effect, and ask the question, does it have an effect, particularly on the compressive response? And I'll consider that, first of all, for the 3D case, the interesting Kelvin foam case. That's the microstructure of various foam structures. And then I'll go back, in a sense, to look at the two-dimensional world of honeycombs. And then at the end, I'll mention the nice feature whereby you can get migration of fluid. Gels, for example, would be at this class. You get migration of fluid through a lattice, and one can get morphing of the lattice itself. Okay, first of all, some introductory remarks that empty microarchitecture materials is now a well-known research topic and an established industry if you're in the game of making running shoes, ultralight running shoes, then lattices are a good way to make them. Nature is good at making woven shell-like structures, and recently additive manufacture come along, but also self-assembly, and we all know how popcorn is made from essentially steaming off of the moisture inside the kernel of corn, and that steam inflates the foam until the foam cell walls burst, and popcorn results. So those examples I've described don't have a fluid phase present, or an incompressible fluid. I'll come on to that. We're now familiar with the so-called Ashby maps, and in this case, if we plot strength against density, you see you can plot lots of materials. There's a historic aspect to this. The Stone Age man and woman started off life in stone, and then more recently, that map is extended and continues to extend. The question I'm asking today is whether by adding an interpenetrating phase, can you fill up gaps in the map? Strength against density is one which has got bounds due to upper bounds, lower bounds, and so on. There are no bounds for fracture toughness against density, so in principle one can go higher. So the question is, how do we use multi-phase lattices to predict and achieve high toughnesses? We've done very little on that, but I think that's still an interesting topic to look at. What has been, of course, of interest to people is the notion of multi-scale, changing the length scale as well as changing the morphology and material. And despite the fact that many of my friends will say small is beautiful, not just economists, but in the world of nanomaterials, I would point out that whilst one can achieve high strength at small scale, if the toughness is set by the cell size, then as the cell size gets smaller, you end up with a smaller, lower toughness value, unless you appeal to bridging or other mechanisms. Okay, so the central question I'm going to ask is, can we improve properties by filling the porosity of a lattice material with another solid? Well, bees have done this. They're not stupid. Well, I don't know how you measure intelligence with a bee, to be fair. But they have made a honeycomb and then filled it with beeswax. Victor, I'm going to give a talk, I think, on this later today. And that application, of course, has a mechanical effect, the presence of the wax and the honey inside the beeswax honeycomb, but also it's got a multifunctional, obvious purpose for storing food. Another area where it's commonly where a liquid is added is the case of plants, where the plant stiffness and strength is controlled by osmosis, adding water, ending up inflating the plant cell, which pre-stresses and stiffens the structure. And we are familiar with the consequences of inflation of the structure of osmotic pressure, that one can get both morphing, and we're familiar with this experience. I shall look at this issue and ask the question, as liquid comes into the plants, what is the stiffening and strengthening that results? I mentioned that bees fill up honeycomb with honey as an energy storage device. Animals such as ourselves, store energy in the form of fat cells, adipose tissue. And adipose tissue consists of closed cell foam, collagen basement membrane, collagen cell walls, if you will, and it's reinforced by collagen fibers, so-called septa fibers, as we see in this sketch. In contrast, and we've all got this, above our fat cells lies the dermis. The dermis is a collagen network. It's a multi-phase collagen network. It's primarily collagen fibers, high volume fraction. They're wavy. Collagen itself is very stiff, stiffness of titanium, and it sort of relies on the waviness of the collagen fibers in order for the modulus of dermis to be about a megapascal, same as that of rubber. So that's how we can move around. It's a fact, and we've measured it. If you look at the measure the stress strain behavior of skin, of the dermis, and compare it with adipose tissue with fat, they're different by a factor of 1,000. So the modulus of the dermis is a megapascal, that of rubber, that of adipose tissue is a kilopascal, a factor of 1,000 less. You don't need much stiffness, excuse me, to fat cells. We looked at injection, injection of needles and also liquid jets into human skin and pig skin too, and the dermis and the sub-layers of fat. And what you find is, for the case of adipose tissue, if a crack is formed by a trouser tear test as shown, and if you look at the crack path, what you see are stretched out fibers. Looking at the crack tip region where it stretches out, here are the stretched out fibers. They eventually tear and pull out. The cell walls of the closed cell foam burst and a crack advances. That's the mechanism of toughening which occurs, the pull out of the fibers in the case of adipose tissue. And the consequence is that the fracture toughness, or the toughness I should say, of adipose tissue is only a factor of 4 less than that of the dermis. So there's this remarkable result that this multi-phase interpenetrating lattice that we've all got is remarkably tough due to the presence of these interpenetrating fibers. Okay, so that's the natural world. Recently there's a move to make artificial sandstones as opposed to natural sandstones. One way of doing it is to precipitate calcium carbonate, which naturally precipitates by bacteria controlling in a particular environment. They will naturally extrude, or exude, I should say, liquid which reacts with the environment and produces calcium carbonate, chalk, and in turn they congregate at the natural junctions between sand particles and give some glue there to bond together the sand particles. Structurally, you can think of this porous aggregate behaving as a lattice. And one measures the fracture toughness, it scales with the mass fraction of the glue. And very simple modeling ideas, whether it's Ritchie Knott Rice or Cohesive zone models, could be used to predict the effect of the amount of glue on the toughness. In the nanoscale world, self-assembly is a useful way of making nanoscale lattices. The nickel gyroid, for example, is a good example. One can make, by phase separation of block copolymers, 2 interpenetrating phases of gyroid lattice. And this is actually a 3-phase structure because some porosity is left. This really is a nanoscale lattice because the cell size is down at 45 nanometers. The wall thickness is, say, 13 nanometers. And one can replace the polymer by various other materials such as nickel. And when you do that and perform an indentation test at this small length scale, you're once limited in the type of test you can do. But if you perform an indentation test and deduce from that the cell wall strength of the nickel, you find that it has attained the ideal strength of the nickel. So this is an example where small scale gives you a much higher strength. The topology of the gyro in that configuration is a so-called bending structure. It's pretty weak in terms of its configuration. So the overall macroscopic strength of this double gyroid is not as impressive as you might expect it to be, but that's because of the knockdown factor associated with the waviness of the gyroid, analogous to I mentioned in the dermis, where wavy collagen fibers reduce the modulus. Okay, so the first take-home message is that the first take-home message that I'd like to point out is that the topology matters, and in particular nodal connectivity matters. The hexagonal honeycomb, if you just look at the nodal connectivity, you see it's 3, and a result which Vikram and Mike Ashby and myself introduced is the sensitivity of the structure to that nodal connectivity. If the nodal connectivity is 4 in 2 dimensions or 6 in 3 dimensions, that's the transition point where you might expect the lattice to switch from deforming in a bending manner to a stretching manner. For the hexagonal honeycomb, it's 3, and so one expects the in-plane response of the honeycomb to be weak and compliant. Whereas if it was much higher, such as a fully triangulated lattice, nodal connectivity of 6, then the structure would be a stretching structure, much stiffer. In 3 dimensions, the nodal connectivity of this Kelvin foam, for example, is much less. It's only, you can add up, it's less, 3 to 4 typically, and it's less than the transition value of 6, and so an open cell structure like this will be compliant and weak. What I'll show in my talk is the result that if you constrain the volume inside the hexagonal honeycomb, you've added a constraint equation, and so it's in a sense behaving as a structure that's now got a nodal connectivity of 4. This constraint of the volume means that it's right at the transition between a bending structure and a stretching structure, and we'll see that. So in some of its response, it deforms in a much stiffer way when it's filled with a liquid and when it's empty. That's not true for the 3-dimensional world, where the nodal connectivity is significantly less than 6, and so the imposition of a constant volume constraint does not change this fundamental result that the structure still wants to bend. But I'll come on to that. Okay. So the question I'm asking is, if you replace a cellular solid's porosity with a incompressible core of no strength but a constant volume, how does that change the response? Do you get rid of all of these interesting features that we know in the world of foams, of crush bands, shear bands, energy absorption, and so on? Well, to address this, first of all, I'll look at the 3-dimensional case of 3D lattices, and then the 2D case, which turns out to be the richer of the 2 cases, the 2D case. But let me begin with the 3D foam. The prototype goes back to Lord Kelvin. He was the one who thought of a minimum energy configuration, periodic repeating Kelvin foam. The Weir-Phelan structure is more recent but not very different in terms of its behavior. But the Kelvin foam, based on the tetrachydecahedron, can exist in 2 forms. It can exist with closed faces, the closed cell foam, or it can exist with the faces removed and just simply the edge struts. And I shall look at the effect of filling the foams with a liquid, both closed cell and open cell. First of all, let's get our reference. So let's consider an empty open cell Kelvin foam. So here's the Kelvin foam. It's a periodic unit cell calculation. I'm going to apply compressive displacements. I'm going to squash the cell and see how it performs. Here's the stress strain response in compression. I've normalized the compressive strength by the cell wall strength. I'm thinking of elastic, perfectly plastic struts here, and row bars relative density. It's the volume fraction of material, typically a few percent. So when the material is deformed, plastic hinges form, and geometric hardening or softening can occur. In this case, geometric softening occurs, and that can lead to crush band formation. So that's the open cell foam. That's well known. Gives our reference. Okay. Now I take the case of an empty closed cell foam. So it's the same lattice, but now we've put some cell wall material into the faces, and here's the response. So again, it's a softening response. It's more evident that the stress strain curve is dropping. So one would expect macroscopic instabilities to occur, crush bands, and so on. The cell faces may stretch in some directions in tension, and in compression, because the cell faces are thin, wrinkling and creasing takes place. But overall, there's a geometric softening. Now I take the case of a filled closed cell foam. So here's the foam. I'm going to fill it with, think of it as water, something which is incompressible, the volume is constant, and now when we load it up, we observe the cell edges will still want to deform, if you follow the Gibson-Ashby argument, in a bending type manner, but the cell faces will stretch. The early response is similar to that of the empty closed cell foam, but what's very different is the subsequent strain hardening. So this is a highly stable response, and again, it's a geometric hardening, and the consequence will be, if you think of the large lattice, that you get a stable macroscopic response without forming crush bands. Right, so what's happened is there's been a change of mode. The macroscopic modulus and peaks in the initial yield strength haven't changed very much, but what's clear is that there's a major change in the subsequent strain hardening response. So let's take a couple of examples. Here is essentially it's a Kelvin foam in the form of a aluminium alloy metal foam, which is filled with essentially an incompressible rubber epoxy. Here's the response. And you can see that what I described in terms of a stable hardening and uniform response that takes place. There's some of the rubber comes out from the edge of the specimen, but essentially the rubber is behaving at constant volume, changes the deformation mode, and the lattice is stable and stiffening. This is an open cell Kelvin foam, as opposed to the closed cell Kelvin foam, which I showed in the simulation. And for reference, as we've seen before, if we don't have a incompressible phase added, then we see a softening response with formation of various crush bands, instabilities. If I plot the stress strain curve and compare them for the open cell foam, it's here, plateau-like behavior associated with formation of crush bands, whereas if I add the rubber to the foam, the measured response goes up to the dashed line. So there's a significant enhancement in properties and, as I said, a stabilization in behavior. Just for reference, the rubber alone would deform in this way and by the blue line, and if we add the rubber response crudely by rule of mixtures to that of the open cell foam, this would be the result. So we have got a synergistic effect, essentially by changing the deformation mode of the lattice. Okay, so that was the case of a metal foam. I'm now going to essentially report similar behavior, but now for additively manufactured by SLA printing of a PMMA type lattice material. Here is the Formlabs response of their grey resin. That's their technical name for it, grey resin V4. If you test the resin alone, the stress-strain response shows significant strain rate sensitivity. In fact, you can think of it as a power law creeping solid with a creep exponent of 9. But reasonable strength here, you see you've got a peak strength in the order of 30-40 megapascals. So you could think of this as a creeping engineering solid, and depending on the formulation, the ductility can be 10% or more of the polymer. So this is a nice prototypical power law creeping solid that one can investigate. We take the same flexible rubbery additive as a core, and you can see it's deforming essentially in a linear manner down at the megapascal level. And so we made a bunch of lattices, and we compressed them. We had control of the lattice in terms of its geometry, dimensions, and so on, and we could fill the lattice, as I said. So just to get a feel for how the response is, just as we saw for the case of the metal foam, one gets crush band formation. In this case, the ductility of the polymer isn't as high as that of the metal, and so fracture takes place. One can get inclined crush bands or just transverse crush bands. Such crush bands cannot form because these lose volume if you were to fill the lattice, and that's what we've done. So here's the filled lattice case, and you can see the remarkable stiffening that's due to the fact that the polymer, in this case the rubber, has strengthened the lattice. Now it's done so in two ways. It's done so because the mode of behavior has changed to an incompressible mode, but also the rubber as it is compressed, you could think of it as a strain hardening solid. So again, there's strengthening due to just the compression of the rubber, and that's what we wanted to separate out, those two effects. Okay. One can vary the relative density, the T over L value of the aspect of the lattice. So here's the lattice. You can vary the thickness of the struts to the length, thereby varying the relative density from 4% up to 14%, and measure for the open cell empty Kelvin lattice the response. And what you see is oscillations in the load curve due to the formation of successive crush bands. We performed finite element simulations of this behavior, but did not put in fracture, and so we did not capture these crush bands that formed due to fracture of struts. But otherwise, the finite element simulations were able to capture reasonably well the modulus and the yield strength. Okay. And as I've already said, once you fill the lattice, you switch the mode of deformation to a constant volume mode, and the stress strain curve, here's the case of 9% as before, as it has got a strongly hardening response. The dotted line or the dashed line is the calculation which shows that behavior. Interestingly, the finite element simulation is somewhat stiffer and stronger past the initial peak, initial yield value, and that's because the simulation did not include the formation of cracks, tears, which one observes. First of all, the mechanism seems to be that at these junctions between the rubber and the struts, the deformation mode involves transverse stretching of the rubber, and so the rubber tears across, and you get isolated cracks in the rubber, which then grow into the struts and get this observed softening behavior. Okay. The question which I I posed earlier was whether the imposition of a core changes the fundamental mode of deformation of the lattice. And from the simulations, when you compare the deformation mode, here I'm just plotting contours of strain. In the empty case, you see hinges forming in the struts at the junction, so that's a bending type structure. When you fill the lattice and impose constant volume to the lattice, one still sees the formation of plastic hinges. So the fundamental notion that the lattice is bending rather than stretching is preserved when one fills the lattice, but the filling process and adding incompressible constraint changes the actual mode of deformation. It's still bending, but it's in a different constant volume mode, and so you can get some strengthening due to that, and more importantly, the subsequent response is much more stable. Okay. I've already mentioned that the EF80 itself contributes to the stiffness, or equivalent to the strength of the EF80 matrix contributes not just from its incompressibility, but the fact it's got finite strength. So if we plot at a strain value of 8%, the strength of the rubber core is here. And if we compare that with the strength of an empty lattice, that's the blue line down here. And I'm plotting this strength of the empty lattice as a function of the relative density of the lattice. So you can see on a log-log scale that the lattice itself is sensitive to relative density. It's a bending type structure, and the simulation suggests a slope of 2. So down at low relative density, the lattice is much weaker than the core, and consequently, whenever you put the core into the lattice to make for this filled lattice, the overall response becomes essentially core dominated, because the core itself is much stronger than the empty lattice. However, when you increase relative density, one sees that the empty lattice is now significantly stronger on this log-log scale, significantly stronger than the rubber, and consequently the lattice dominates the response. So it's somewhat complicated, this behavior, because whenever you fill the lattice, you do two things. You add the strength of the core, the CF80 core, but you also impose incompressibility. And this is the net effect. Okay. In order to try and probe whether the lattice itself is behaving in a much stronger manner when one puts in the incompressible core, a way to do that is to take the observed stress-strain curve of the filled lattice, subtract off from it the contribution, thinking of this like a Voigt per bound style rule of mixtures. So subtract off from the stress-strain curve of the filled lattice, the stress-strain curve contribution due to the volume fraction of the core times the stress-strain curve of the core, and you're left with this lattice contribution. So we can use the observed lattice stress-strain curve, the observed core contribution, and deduce how much of the macroscopic response is coming from the lattice. And when we do so, we can get a plot of that against relative density, and we can compare that plot with the stress-strain curve just for the empty lattice. And thereby we can ask the question, does the core, the incompressible core, actually change the effective strength of the lattice? And the answer is not by very much, a little bit. So at a strain level of 8%, a bit above the yield value, here is the empty lattice response. I'm plotting stress against relative density. And on the right-hand side, I'm plotting the contribution to the macroscopic response of the filled lattice due to the lattice itself. And you can see in both cases the slope is well above 1. 1 would be closer to 2 here and 1.6 here for the filled lattice. A slope of 2 would be consistent with bending type behavior. And that hardly changes when we add the incompressible core. So for the case of these three-dimensional lattices, the take-home message is that the fundamental mode remains bending, but in a mode which is not constant volume. So you get some strengthening, but the important feature is the much more stable behavior. Okay. One can ask the question, which has been asked sort of many times in the case of an empty lattice, how big a specimen do you need in order to probe the material properties of the lattice, of the foam? And the answer is not many cells. So if we take a single unit cell and either do simulations or experiments, in this case it's simulations, a single cell has got a stress strain curve in the empty state here and in the filled state here by the black line. As you make more and more cells and build them up and go to the infinite case of the periodic cell, you find that there's some elevation in response, but not very much. This again is for that rubber EF80 core being present. And the physical explanation is that there is a little bit of side leakage out, but only over one cell dimension. And so very quickly, you don't need many cells in order to capture a stabilized response. One can analyze this by a shear-like type process. It's reminiscent of in soil mechanics when people talk about on-drained and drained test, where in the on-drained state there's no liquid migration out of the structure, but with time the liquid might, whether it's water in the case of the soil, can migrate out the side of the structure and produce a drained response. And here, because the rubber has got a comparable strength to that of the empty lattice, there's not too much side leakage of the rubber. Okay, so what I've talked about is the three-dimensional world of a lattice that happens to be the Kelvin unit cell. Now I want to change our focus to that of the two-dimensional world. And in a sense, we thought this would be an easy warm-up problem. It turned out it was a hard warm-up problem. And it was really, and you'll see why that is, the finite element simulations, numerical simulations, were difficult to get in an accurate way because of the formation of various instabilities. So we took a two-dimensional honeycomb. Just for reference, I'm plotting here the stress strain curve of the empty hexagonal honeycomb. So if I take, and there's a major parameter here, is omega, the inclination of that cell wall. For a regular hexagonal honeycomb, omega is 30 degrees. But we can vary that and end up with an anisotropic honeycomb. So if it's 20 degrees, that value is less. And we can also take 40 degrees, in which case it's greater than the regular hexagonal honeycomb of 30 degrees. For the empty case, I'm showing here the compressive response. And in all cases, for all values of that inclination omega, one gets a softening behavior, loss of volume, bending type response here in compression. Here's the bending type response. And this is our familiar friend in the sense of how crush bands will form in an empty honeycomb. If we take the same honeycomb and put it in tension, again, plastic hinges form. This is what you get if you take a hexagonal honeycomb, chicken wire, and pull it. You stretch it out, and geometric hardening takes place with lockup. And the rate of hardening depends upon the initial orientation, the initial value. It's delayed if omega is small, but in all cases you get this strongly stable response. So so there's a strong geometric effect here, and I don't know how well appreciated it is, but many people just do, excuse me. Many people just do compressive tests, get these crush bands, But the tensile response is very different from the compressive response. This is for the empty honeycomb. Now if we add an infill, what happens? Well, the first way to think of this problem is to say, let's plot the volume of the hexagonal honeycomb as a function of omega, that angle omega. 30 degrees, which I've marked, is the regular hexagonal honeycomb case, and it's an extremal structure. It occupies the largest volume V for a given length of cell size is not changing. So if I just imagine a pin-jointed framework, pin-jointed truss, each cell is length L, and I vary that angle omega, I see that as I increase omega, I go through a maximum inflated volume, and if I continue to increase omega through 30 degrees, the volume drops. So that is telling us something very important. It's saying that fundamentally, the lattice, I think it was pin jointed, can easily form by a mechanism. It can deform, but once it gets to its maximum inflated state, where omega is 30 degrees, if I continue to try and deform the structure, the volume can only decrease. So we have to switch mode to a stretching mode at 30 degrees if we were going to continue to try to expand the lattice. The consequence of that is huge. So if we look at the compressive Young's modulus of a honeycomb, by filling it now with an viscid liquid, so we take our beeswax, fill it with viscid honey, if that's possible, and plot modulus against omega. For this case of 30 degrees, for this spot value, the modulus is very small because for that one value of omega, the Poisson ratio is 1 in plane. So the honeycomb itself can deform at constant volume, and we're just picking up the bending response in this first increment of 30 degrees. At any other value of orientation, if we constrain the angle, if we constrain the volume, constrain the volume to be constant, and calculate the modulus, we find that necessarily the constant volume constraint means that the cell walls must stretch, and you end up with a much higher modulus of the honeycomb. So the presence of the constant volume constraint has a huge impact upon the stress-strain response. Right, let me try and explain that in a little bit more detail. If we first of all think of when I say modulus, let's be more precise, we have an orthotropic, anisotropic solid if omega is not 30 degrees. So I need to distinguish between the in-plane shear response, my axes 1 and 2, mean that I can talk about a shear modulus G12. And if I shear that lattice with a constant volume, because it's in shear, the response will be at constant volume, and so I don't need to worry about the presence of the liquid, and I'll be measuring the shear response, and that's a bending structure, all at constant volume. And I can plot that here in this dotted line. So that is the shear response. The shear modulus scales with relative density cubed as a function of omega. So this is the shear response either of an empty or of a filled honeycomb. If, on the other hand, I ask the question, what is the axial response, as opposed to the shear response? If the honeycomb is empty, again, it's the modulus scales with relative density cubed, and here's my dotted line to show that. If, on the other hand, I fill or put a liquid in and constrain the response to constant volume, I get the line you saw from the previous graph of modulus against omega. I switch to a stretching behavior. So the presence of a volume constraint has a major effect upon the structure. Now, by way of example, I will talk about the plant cell. One way to think of this is in the flaccid or in the relaxed state, where omega is not 30 degrees. The plant cell has got a smaller volume. When osmosis comes along, water comes along and diffuses into the cells, the cells inflate and they would like to go to this inflated state of 30 degrees for omega. And once they get to this inflated state of 30 degrees, the structure is then fully inflated, and the only way it could continue to deform is by a deformation mode which involves stretching of the structure. And consequently, the plant cell switches from behaving in an open cell manner to one of being a constant volume mode of deformation, which takes you from this dotted line, which is the empty mode where volume can change, to the black line. Notice the difference in normalization. This is rho bar cubed, so this is actually a very low modulus, whereas the black line is normalized by rho bar, the relative density, and so the response is much different. So constant volume constraint has a major impact upon response. We asked the question, what about the effect of volume constraint upon the yield behavior? And for this idealized case, one can write down an exact analysis and predict the yield surface, the initial yield surface. And what you find is the yield surface is very sensitive to the omega value, and particularly in the vicinity of omega 30 degrees, the yield response is very sensitive. One can derive the analytic equations for this. In practice, when we do the experiments, there's an added bit of physics which can come in. And the added bit of physics is non-trivial. It's the fact that cavitation of the core can take place of this honeycomb. And you can think about it in two ways. You can say if the honeycomb wants to inflate, or wants to dilate, I should say, with tension in the liquid, then bubbles could form, cavities can form, and the liquid, the core could actually increase in volume, or peeling could take place between the core and the volume. So the added physics is, when you do the experiments on these lattices, is it's very hard for the core to maintain constant volume if the cell wants to expand, because peeling, cracks can take place, cavitation can take place. So there's this notion of cavitation of the core being important. To show that, let's take the case of, let's just deal with the compressive case. Here is a non-cavitating core. So I'm going to keep constant volume. I've got omega is 40 degrees. I have this strongly softening behavior. And when we look at the simulation, you get what looks like a kinking type behavior, rotation of the cell structures, and you switch, and you have a very strong softening mode, which we can calculate analytically as well as numerically. That's the case of a constant volume behavior. If, on the other hand, we allowed cavitation to take place, and by that I mean think of this as the core, 40 degrees as the orientation. Here I'm allowing separation to take place that wants to take place, and you see what happens is you get a very different response. Essentially, the lattice is behaving closer to an open cell lattice. It can increase in volume, but once the volume comes back to the initial value, lockup takes place, and the structure is much different. So this filled lattice is behaving as initially as open cell, but once the volume goes back to initial value, lockup takes place, and it now then deforms as a constant volume lattice. So there's this important aspect of physics, which is that cavitation, whether cavitation takes place or not in a core, has a major effect on the strength. If you think of an experiment where you apply surrounding hydrostatic pressure that's large enough, then you will switch off this cavitation mechanism. So when we allow the cavitation to take place, put a little imperfection into the lattice to try and trigger whatever soft modes it wants to form. What you see are You can call them shear bands where there is a slight softening which takes place. It's not huge, it's just a small amount of softening. And although you can say that this is a localization problem and so on, the degree of softening is small and quickly lockup takes place, so it's not very far away from elastic, perfectly plastic solid. If we contrast that with the case where we keep the volume of each cell constant, this is a non-cavitating case, constant volume inside, we dramatically change the response. We have initial behavior, which is stretching, gives a high peak load, but then after that, the lattice rotates into a bending mode, strong softening takes place, and one would anticipate from this periodic unit cell response, this very strong softening behavior, that you would get lots of instabilities. If you consider, for example, a case where you take a structure with a missing cell, and when you do so, this is indeed what we see. We see a high initial peak load, but then the formation of essentially a shear band, it's a constant volume, then propagation taking place of the shear band. I'll mention, because we've done a lot of work in this in the past in fiber microbuckling, when you look at this image, it looks in many ways like a fiber microbuckle. You get an inclined kink band. In this case, the material is deforming at constant volume, and you get propagation of the kink band first across the specimen. And then band broadening takes place. So this is exactly what you see in fiber composites. And the mechanics is rather similar. This instability is due to this strong softening and then lockup behavior. So if we take an idealized case of saying that band is one of a shear band, so let's take the case of thinking of the honeycomb subjected to shear and evaluate its shear stress strain response. We will see in a second that the response is of this type, where you get a softening and a hardening. You can calculate the so-called Maxwell propagation stress as a line, a horizontal line, where the area above it and below it are the same. This would be the shear stress that's needed to take you from an unlocked initial undeformed state to a fully deformed state, and is the propagation stress that's required in order to propagate this shear band along its length or indeed laterally. So one can think of reducing this problem of a shear band propagating by just thinking of it as a problem in shear, as shown, and then by using essentially Moore's circle, go back from the shear stress that's on the band to the uniaxial stress just simply by stress resolution. And that gives us the axial response, the axial stress, and equivalently the Maxwell stress, the axial stress, in order for such a shear band to propagate. So here's the simulation, infinite element simulation of such a shear band. When you apply shear stress to it and follow the response of material in that shear band, you indeed get a shear stress against shear strain response, which is softening and then hardening. One can write down the horizontal line or construct the horizontal line and thereby calculate the Maxwell stress that's required in order for this instability to propagate. Here's the final element simulation just to show what's happening in this shear band, and TP is the deduced average horizontal stress, as I said. And you can use that calculation of the Maxwell stress to estimate the plateau stress that's observed in the simulation. So the simulation I'm now talking about is the compressive loading of a specimen, say with an edge imperfection, and you see that the shear band propagates across and then band broadening occurs. Here's the simulation, which I think I showed before, of the axial response. The plateau value of that stress can be directly related to that shear stress, the Maxwell stress in shear. And when you compare the two calculations, one of the structural response and one of that separate Maxwell stress evaluation, there's good agreement between the two. So there's a very close analogy between this instability propagation of a shear band in the non-cavitating honeycomb with his strongly softening behavior, followed by an instability which can be well modeled by the Maxwell stress. Okay, this brings me in the remaining couple of minutes to the final part of my talk, which is to ask the question. So far we've talked in the passive world, if you like, of taking a lattice, understanding the mechanics when the lattice is either empty or filled. We've pointed out there's a strong effect of adding volumetric constraint. So now let's have some fun. Let's make a bathroom sponge. So this is being done, depends what your idea of fun is, I suppose. So this is the commercial way that cellulose foams are made, and then often they're transported and sold in this form. You take cellulose fibers, you add sodium sulfate crystals, which define the cells, this three-dimensional foam. You melt out the sodium sulfate crystals and then compress and dry the structure. And you end up with something which looks like cardboard, cellulose cardboard structure, but actually it's got compressed cells in it. Then, once you ship it and add water, it activates. And the volumetric actuation is a factor of 10 or more. So the structure reinflates to the cellulose structure of the bathroom sponge. And you can see this experimentally. If you take the compressed cardboard-like structure as shown here, you don't see any voids, any bubbles in it. But if you now add a droplet of water, a side view, see the water absorbs in. Then expansion takes place as the foam inflates due to the presence of moisture, by a factor of 10. The side view shows something which is interesting. The expanded wet foam here the water hasn't penetrated, hasn't diffused all the way through. But the foam, as it expands, soaks up the water like blotting paper, inflates as shown, and the underlying material is left untouched. Well, how do we analyze such a behavior? The way the initial steps would be, first of all, to separate out I've just taken a little bit of the cellulose foam here in the compressed state. I've dropped it in water, and you can see this huge expansion by a factor of 10 or more. So that's the expansion phase, just due to hydration of the foam. Suddenly, when I say suddenly, it's between 0.1 and 0.5 seconds it takes for the foam to expand back to its initial state. But in order for the water to get to the foam, if the foam is not small but it's a larger specimen, then, in this case I'm putting water in the bottom of it, water has to diffuse in, it has to migrate through the foamed state, so we now have damp foam in this region, and when the water reaches the dry foam ahead of it, it expands. So you see this process is one of diffusion of water through the damp foam, followed by the actuation, as I'd shown in this image below. That gives you a height against time curve, experimentally as shown, and one can develop a model. I don't have time to go into it, but the theory would talk in terms of diffusion of water through the damp foam, followed by actuation in order to expand it, to give you this large factor of 10 in terms of expansion of the foam. But time dependent for two reasons, the expansion and the diffusion. Okay, so this takes me to my last slide, just to list the main conclusions of my talk, which are that filling of a core, even with a liquid of no strength can impose a huge effect upon the response. That's particularly true for the hexagonal honeycomb when the nodal connectivity of 3 was close to the transition value of 4. When you add water and constrain the volume, you essentially reduce the degrees of freedom in the system, and the structure may now have to deform by stretching as well as instead of bending. I pointed out that in the non-cavitating case of constant volume, this feature can lead to strong instabilities. Inclined shear bands can form that can be analysed by a Maxwell construction, much as we did in the past for the case of fibre composites. There is yet still to be done, much to be done, I think, particularly in this interesting world of diffusion or migration by whatever motion. It may be capillary rather than diffusion, but this motion of liquids through the structure, and then once the liquid gets to the interface, a reaction taking place, leading to the propagation of an actuation wave through the structure. And on that note, I'll finish. Thank you for your time.
Thank you very much, Norman, for this excellent talk covering such a wide range of topics. We have about 5 minutes or so in the schedule for questions, so please, the floor is open to the audience for questions. Okay, so that's it.
Thank you very much for the talk. I'm right here on stage right. It was obviously very sophisticated, but also very accessible as a non-specialist. Can you comment on the effect of friction or bonding between the core and the lattice, especially in the case of rubber or epoxy?
Look, only to say that this was all idealized stuff because we did not, we wanted to take the 2 extreme cases of fully bonded or fully unbonded and explore the significance of that. And so that remains a topic to be explored, so I can't really comment more than that.
Norman, excellent lecture, congratulations. Number of new results. You can anticipate my question. Is there an effect of size of the cell, given the softening within the plastic inches, for example? And is there an effect of the size of the specimens, which have softening, that will change the results?
So, I could mention just the, remind us that the, when we thought of those self-assembled nickel gyroid structures done nanoscale, you could think of them as at the cell wall level bending structures, and the strain gradients associated with bending increase the strength of the lattice. So whenever a lattice has got a strain gradient of bending of hinges, the hinges are behaving in a stronger manner due to size effects than you would anticipate if you didn't think in terms of, say, gradient plasticity. I don't know if that answers your question.
Yes, okay, thank you.
Norman, here it is. Just beautiful, and so clearly described. My point is, if you have partially filled rather than completely filled,
Yeah.
You get back probably the unfilled result, like you have shown with cavitation.
Yeah.
So is it something like we could think of like a phase transition where when it just filled, then you switch the property, even small unfilled region will get it back to the unfilled state.
So, yeah, let me say it this way. If you parch, and you could do this at home quite safely, you could take a bag of crisps and replace the crisp with water, so you've got a partially filled bag. And in certain modes, the bag will want to expand, and it can do so because it's partially filled, and it can do so. But I guess what I'm saying is in one mode, and it could be in compression, that you get the water's not doesn't have any effect. But in the other mode, in tension, where you're reducing the volume, then it kicks in. So it's a one-sided constraint. So so the point is that in a partially filled state, when you want to inflate the bag some more, it will happily do so as if it was an open cell structure. But if you want to reduce the volume, you bang into the constraint.
I see. So it's kind of
Yeah, it's a very different response
Tension
in
compression.
tension compression. Once you get to the fully inflated state, there's different.
It balances out. For the cavitation, don't you need a very high tensile stress?
Okay, so we know from way back that the cavitation stress for a solid is typically 5 or 6 times the yield strength of the core material. The core, I didn't say this, but in final element simulations, the core might have had a strength of 10 to minus 3, 1,000th that of the lattice material in the numerical simulations. So the actual cavitation stress that you would get is small, just because the core has got a very low strength and no modulus.
Thank you.
All right. Thank you. A very inspiring and wonderful lecture. So my question is, in your 3D cases, you conducted compression tests on the 3D field and the empty cells. But my question is, if you change the loading from compression to tension or other types of loading like shear loading or torsion, how the field forms perform differently from the empty ones? Thank you.
Yeah, okay. So I didn't have time to go into it, but all I talked about today in compression has also been on tension. And it goes back to the point, one way to say it is, as I said a second ago, that if in compression, when you compress, you may hit that volumetric constraint, say for the, but in tension, you may not. But one way I could think of saying it is, for the omega value of 40 degrees that I focused on in compression, if you take out now a lattice, it's 20 degrees of omega value. In tension, it behaves pretty much the same way. So there's this geometric reflective symmetry. So 20 degrees orientation of inclination and tension is like 40 degrees in compression.
So, we are sort of running out of time, but Norman is here for the conference, and I'm sure we'll be happy to answer questions in the breaks, etc. So we just thank Norman once more, and